epsilon pretty small, you understand why I only took epsilon to be 0.2. Because if you're nervous and you want to get a good result and you take epsilon, say, to be 0.1, forget it. You can't see any difference between the curves. And the only interesting thing that happens is if you take epsilon bigger, so now there's a bigger crack opening up between the exact solution and the WKB approximation. Oh, yes, and one other thing, I emphasize that we're very lazy here. This was just, a few boards of class calculation. We could have done the same thing with a higher order WKB. We didn't have to do just leading order WKB. This is just leading order WKB. This is just the physical optics approximation where we throw away S2, S3, S4, forget that. But we could have included them, but we clearly didn't really need to include them. And even for large epsilon, you have this wonderful approximation. Look how good that is. I mean, this is where there isn't any epsilon anymore. Epsilon is 1. So this is pretty good. Okay, but this is not really the complete problem that we wanted to solve. Because if you remember, the problem that we want to solve is the eigenvalue problem. Okay, so the eigenvalue problem says V is some potential that looks like this, and we're looking for the energy levels. Here's E0, E1, E2, and how do you find the energy levels in this potential well? What are the quantum mechanical energy levels? And what we said was, if you put an energy, E, in this potential well, and you're solving the Schrodinger equation, which is minus d squared dx squared plus v of x psi equals E psi, okay? So V is this potential. E is some energy that we put in the well. Not necessarily one of these eigenvalues, just some energy, okay? And we say, let's take Q is equal to V of x minus E, okay? Then we are solving the differential equation minus psi prime prime, that's plus psi prime prime, equals Q psi. We said to solve this equation, we would use WKB. So we insert right over here a small parameter epsilon. And we understand that putting the parameter here is a strange and singular thing to do. Okay? It is strange because when it goes to 0, there is no unperturbed solution. There just is no unperturbed solution at 0 because this is no longer a differential equation. Okay? It's not a differential equation. So this is an interesting and singular way of introducing epsilon. So why do we do it? Because we think it has some physical significance, because there's an h bar over here. Notice I've got an h bar over here, but in my units, h bar equals 1. It's a dimensional parameter, so I don't have to write down 1. Okay? But when you set epsilon equals 0, in some sense, you're taking h bar equals 0, and that's the classical case. So we're somehow, for small epsilon, we're getting closer to the classical result, whatever that means. That's a very subtle issue. Okay, but that's why this is called a semi-classical approximation. So what are the boundary conditions? Here's the differential equation, but in order to have an eigenvalue problem, you have to have boundary conditions. So the boundary conditions are that psi of plus infinity is equal to 0, and psi of minus infinity is equal to 0. And this is a very hard problem, because you see, if this is the energy is, this is the potential V of x, the energy is equal to the potential not 1 time, but 2 times. So we have a two turning point problem. There's one turning point problem over here, and one turning point over here, and one turning point over there. Okay, two different turning points. Okay, and that's pretty fancy. Okay, that's really pretty fancy. We could call this turning point alpha, x equals alpha, okay, and this turning point is x equals beta. How in the world are we going to solve that? Look at how much trouble we had solving just a one turning point problem. But we did get the answer. So what we're going to do is really clever. We're going to put together two one turning point problems. Okay? So how are we going to do that? We're going to say there is a region. This is the thing. Do we have that colored chalk in it? Oh, too bad. Okay. Oh, wait, there probably is here. Cool. Oh, right. Yeah, that's cool. Is that boring? Or is that, no, this is okay. So, so over here, you remember this was our region 1. And in the vicinity of the turning point, that was our region 2. And you remember there's an overlap of region 1. So region 1 comes all the way down here. Region 2 goes all the way up here. And there's an overlap. And then region 2 extends down here. And then region 3 overlaps with region 2. And all of this is region 3. And all of this was a one turning point problem. So let's write down the solution to the one turning point problem. Okay? So the solution to this problem over there would read, well, in region 1, y is approximate, or psi, we're calling this psi, I guess. Psi is approximately c, some constant, we don't know the value of that constant, okay, over q to the 1/4, okay, times e to the minus 1 over epsilon integral from, now before we had the turning point at 0, so it was the integral from 0 to x, but the natural place to integrate from, the only interesting point, is the turning point itself. So let's integrate from beta up to x dt square root of q of t. And that is region 1. And in region 2, well, who cares about region 2? Okay, we already did that. So in region 2, psi is proportional to c times blah, blah, blah. Okay, we're not going to write down that formula because it's just an area function. Yeah?
So why do we not care about region 2?
Because, oh, we do care about it, because, but we did that yesterday.
Right.
Okay? So the point is that what happens in that turning point region is very important. Why? Because it tells us how to go from there into region 3.
Right.
Okay? But it's really only region 3 that we're going to care about. Okay? So the point is that 3 came out simple again. It was, again, another WKB function. This time, however, in region 3, you see that V is smaller than E. It's smaller than E. So V minus E is a negative thing. And I only want to deal with positive things, real positive things. And so therefore, psi in region 3, it came out. The only interesting thing that we learned is that there's a factor of 2, not 1, but 2c, times a 1 over q to the minus 1/4, but q is negative. So I will absorb into this constant here some complex number, and I'll write down minus q. to the 1/4 because minus q is a positive number, and that's the thing I'm going to take the 4th root of. Okay? And then instead of an exponential, there are two possible exponentials. You know, e to the square root of integral square root of q and minus integral. But q is negative, so it's e to the I times something and e to the minus I times something, which is a linear combination of sines and cosines. And the correct linear combination that connects to the Airy function is sine of 1 over epsilon times the integral, I'm integrating in the positive direction, from x all the way up to beta, dt square root of minus q of t. But there's a phase shift. Okay, it's a particular linear combination of sines and cosines, and there's plus pi over 4. And that's the solution that we got. Okay? Now, that was all the work we did yesterday, but it's not enough to solve this problem, and the reason is that yesterday, region 3 extended all the way down to minus infinity. You see, this keeps oscillating all the way down to minus infinity. But that's not what happens in this problem. In this problem, it would eventually bump into this turning point, and this would cease to be valid. So here's what we're going to do. We're going to solve another one turning point problem. Okay? I like this. We're going to get some more color. That's the orange guy. How about a blue guy? Cool. Okay. So let's solve another one turning point problem, except this is a backwards one turning point problem. Instead of the solution, notice this guy here is constructed so that psi goes to 0 as x goes to infinity. Notice, because there's a minus sign here. Okay? Oh, by the way, all these are asymptotic signs. All this is valid as epsilon goes to 0. That's very important. So we're going to solve another one turning point problem. Here is going to be the new region 1, blue region 1. This is the orange one. Whoops, orange. This is the orange one here. And now we have a blue region 1 and a blue region 2. Notice the overlap. And a blue region 3. And I should be careful here. Don't, for a moment, think that this blue region can extend as far as that turning point because the solution will break down. Okay? So what does it look like in region 1, region 2, and region 3? Well, in region 1, the solution, I always want to integrate in the positive direction, so psi is going to be proportional to some constant. Now, it's not this constant. It's just some constant. Okay? D, we'll call it. And D doesn't have anything, at this point, nothing to do with C. Okay? D over q to the 1/4. And then there's an exponential, e to the minus 1 over epsilon, integral from x up to alpha. Notice I'm integrating in the positive direction. So this is a positive integral here, dt square root of q of t. And then in region 2, psi is going to be proportional to, well, who cares about all that junk? Airy, blah, blah, blah. Okay, we don't need to write down that function. Notice, by the way, that, let me just say it explicitly, psi goes to 0 as x goes off to minus infinity. That's very important. Okay, so this is how I satisfy this boundary condition. So the first one turning point problem satisfies that boundary condition. Second one satisfies this boundary condition. Now, in region 3, what does the solution look like? It looks like 2d over minus q to the minus 1/4, or to the 1/4 divided by minus q to the 1/4. And then there's a sine function, and the sine function looks like 1 over epsilon, integral from alpha up to x. You notice I'm integrating in the positive direction, and I'm integrating something that's positive, dt square root of minus q plus pi over 4. That's what the solution looks like. Okay. However, here's the point. The point is that in turning point problem number 1, that's valid all the way down to, but not right down to, not exactly down to this turning point. And the blue solution should be valid all the way up to, but not reaching that turning point. So now we're going to match together this asymptotic approximation, this one right here, in the classically allowed region, with this one right here, okay, in the classically allowed region. These have to be the same, okay? If there's any sense to what we're doing, this is representing the same function. These guys have to be the same. So let's see if they are the same. Okay? You think they're the same? Well, let's see. First of all, there's a factor of 2, and there's a factor of 2. Well, that's the same. There's also a minus q over here, minus q to the 1/4 in the denominator. Here's a minus q to the 1/4. That's the same. That's good. But they're not quite the same because you notice in the argument of the sine function, we have an integral here from alpha up to x. Whereas over here, we have an integral from x to beta. That's not the same. So let's try to force it to look the same. We could rewrite this. Let's push this up a little bit. Okay. So we could rewrite this as 2d minus q to the 1/4. And there's this funny sine function. So if we want to make this begin to look like that, what we would have to do would be to integrate all the way from, not from alpha to x, but from alpha to beta. Let's do that. 1 over epsilon integral from alpha to beta dt square root of minus q. And then we'll compensate for that by subtracting off what we just added on, which is the integral from x up to beta. Okay, dt square root of minus q. And then there's plus a pi over 4. That's not quite good enough, is it? Because there's a 1 over epsilon here. There is, you notice, an integral from x to beta here. But this is minus an integral. Not so good. All right, why don't we do this? Why don't we put a minus sign in front and then put a minus sign inside of the sign? The sign is an odd function. Okay, so that would give us a minus sign here, a plus sign there, rats, but a minus sign over here, rats. That's not right, because over here there's a plus pi over 4, and here's. How about fixing it up even further? Let's make this plus pi over 4. Let's put a plus pi over 4. Add a an additional pi over 4, and subtract a pi over 4. So that makes this pi over 2. Okay, so now take a look at this. This is the orange approximation. Okay? And when we go over here, it's now beginning to look like the orange approximation, isn't it? Okay? This part of it is in exact agreement with that. Okay, do you all see this? But there's some junk left over. This junk right over here. Now, if this junk were 0, then this asymptotic approximation would be in exact agreement with this approximation, with the simple constraint that minus 2d would be equal to plus 2c. Those constants are arbitrary. We're done. It works. However, this underlined stuff over here couldn't possibly be 0. Why? Why is that? Why is this not possible to be 0?
You can choose any epsilon.
Say it again?
You can choose any epsilon.
No,
Sure.
both are negative.
But there's this, even for any epsilon, this couldn't be 0. Why?
Both are negative.
Both are negative.
Well, that's a negative number, right? And q minus q is positive, so this integral in the positive direction would again be a positive number multiplied by minus 1. So it couldn't possibly be that this negative number here and this negative number here could add up to 0.
Don't you have epsilon being negative?
No, no, we want epsilon to be positive. If epsilon were negative, then, you see, you would be violating this condition here. We're assuming that epsilon is positive because we want to satisfy the boundary condition that the eigenfunction goes to 0 at infinity. If epsilon were negative, this would be blowing up. Can't do that. So this is valid to be precise. We haven't been precise about this, but it's valid as epsilon goes to 0 through positive values. Okay? It's a one-sided asymptotic limit. Okay? So we can't make this thing 0. So does this mean we can't solve the problem?
No.
You say no. Why not?
We can make it a multiple of 2 pi.
Or, you could certainly make it a multiple of 2 pi, or how about a multiple of pi, an integer multiple of pi? If it were an integer multiple of pi, then when you take sine of something plus n pi, that just gives you minus 1 to the n. Right? Now, if it were 2 pi, then a multiple of 2 pi, then minus 2d would be equal to plus 2c. But if we're a multiple of n where n is odd, then there would be an extra minus sign. So 2d would be equal to 2c. Okay, so in either case, that works. But if we want to include all the possible values, it follows that this must be a multiple of pi, not 2 pi, just pi. Okay? So what I'm saying is, let's push this up. So what I'm saying is, we can make this be a multiple of pi. Let's require that 1 over epsilon, integral from alpha to beta, dt, square root of minus q, plus pi over 2, is some multiple of pi, n pi. And because this is a positive number and that's a positive number, this would have to be a positive multiple of pi. Here, n would have to be 1, 2, 3. It couldn't be 0 pi or minus 4 pi or something like that. Okay? That's the condition. Okay? And you notice that there's a pi over here. Okay? So I could subtract this pi, and I could require that 1 over epsilon integral from alpha to beta dt times dt square root of minus q of t. This is equal to n minus 1/2 pi for n equals 1, 2, 3. Or the way you usually see it in books is not n equals 0, 1, 2, 3, but really what books write, they do a shift of n, and they say, let's make this into n plus a half pi, but now let n go from 0, 1, 2, 3, like that. Okay? And if this is the case, then that says that c is equal to minus 1 to the n times d. Okay? And now, if this is true, this is the constraint. If this is the constraint, then we have solved the two turning point problem. This is the condition on Q that says a solution actually exists. If this is not true, there isn't any solution to the two turning point problem. So that's the constraint. But I want you to notice that buried in Q, inside of Q, is the eigenvalue E. Okay? Buried inside of Q is that eigenvalue. And this says that the only eigenvalues that can solve this equation, I mean, this is a discrete number, it's an infinite number of possible equations, but it has a discrete integer n inside of it, and that's where quantization comes from. Okay? You see that quantization is intricately linked with asymptotic analysis and subdominance. Okay? And we obtain the quantization formula in here. This says that the solution to this problem, it will be written, it will be called E sub n. That's the nth eigenvalue. So if we can solve this equation, we have found the eigenvalues. Okay? That's where quantization comes from in quantum mechanics. Okay? And we solved, once again, using asymptotics, we have solved an eigenvalue problem approximately. Okay? Now, yeah, you have a question.
But, so there are some specific values of epsilon where you don't have to have quantization.
There are...
I mean, so you could fix your epsilon to be something specific to get a multiple of n plus a half pi.
Right. That's
so
right.
Could you
However,
solve any problem without...
That's right. If you are going to allow epsilon, you could say this is an equation for epsilon as well, if you wanted. Okay? And so, but you see what you're doing. We only want to solve one problem. We want to solve the unique problem back here where there isn't any epsilon. Okay, where epsilon is 1. But I completely agree with you. If you allow epsilon to vary, then, of course, you have, for each epsilon, you could allow E to vary as a function of epsilon. That's what it says. But we don't want to do that. We want to say, let's begin with a unique problem and let's find the eigenvalues for that problem. Or another way of saying is, for each value of epsilon, we would like to find the eigenvalues. And then they are discrete and they satisfy this condition. But you're right, if you want to allow epsilon to just vary, you can think of this as an equation that determines epsilon. Okay? So you give me E, and you find the epsilon such that that value of E works. That's perfectly okay. Okay, but we are treating epsilon, all of this is being treated in the limit as epsilon goes to 0, right? And so there's a little tricky aspect here to this. This is not an equal sign. Okay. This is really an asymptotic sign as epsilon goes to 0. Okay, yeah.
And but we are interested at the end of the day as epsilon equals to 1.
Right.
So that means that we are looking at E large values of 0.
That's right. That's right. We're going to see that. I'm going to show you that. Okay, so in fact, we want epsilon to be 1, and we want to replace the limit as epsilon goes to 0. This is the subtle change that's going to occur. There's going to be a transmutation in the asymptotic limit, which we haven't seen yet. Okay, so what I would say is this. How do you think about this problem right here? Forget E completely. Imagine that you're really solving this problem. And we're asking, is there a solution to this problem? Okay, that satisfies these two boundary conditions. So there's just some arbitrary function in here, Q. Is there a solution to the problem? No, in general, not for all functions Q. only for those functions q that satisfy this constraint. Only for those functions q. Now, indeed, q contains the energy, E, the eigenvalue E. Okay, so what we're then going to do is something very fancy. We're going to say q, the components of q are v minus E. We're going to fix v. We're going to say, let's work for a fixed function v. But we will allow E to vary, and that is going to be the thing that we're going to determine in the end. Okay, so but I'd like to do a very simple example. This is the standard example that you do in all elementary physics courses. What you say is, very simple, you say, suppose v of x is x squared over 4, for example. What problem am I now solving? So this is example. What are we looking for? V is x squared over 4. What is that? This is the harmonic oscillator. Okay. So this is the general solution to the problem, but let's look at the harmonic oscillator. If v is x squared over 4, then I ask you, what is alpha and beta? We have to find alpha and beta. So those are the turning points. That is where x squared over 4 is equal to E. It's where v minus E equals 0. So therefore, x is equal to plus or minus the square root of 4E. Okay? And that is alpha and beta. So alpha is minus the square root of 4E, and beta is plus the square root of 4E. Okay? And so there's alpha, there's beta. So this condition reads 1 over epsilon integral from minus the square root of 4E to plus the square root of 4E dt square root of, now this is, q remember is v minus E, but this is minus q. That's E minus v. So this is E minus x squared over 4. And this is supposed to be equal to, or asymptotic to, n plus 1/2 pi. Okay? And the question is, are we smart enough to do that integral? Okay? So to begin with, I think a simple thing to do with the integral is to say, look, that integral is, the integrand is even. And we're integrating from minus to plus, right? So let's just integrate over the plus values. So let's take 2 over epsilon, integral from 0 to the square root of 4E, dt, square root E minus x squared over 4, and that's n plus 1/2 pi. That's a small simplification. Let's push this up. Sorry? T. You got it. This is T. Good. Okay. That looks like a plus sign, but it's really a T. Okay. Now, we've made a little bit of progress. How about making another small amount of progress? Let's make the substitution, instead of integrating over T, let's say T is equal to the square root of 4E times S. Little change of variables there. So that gives me 2 over epsilon, and dt becomes the square root of 4E times ds. And now the integral is going from 0 to 1. That's nice. And inside the square root sign, we have the square root of E here, and t squared over 4 just becomes E times s squared over 4. E times s squared, E times s squared, not over 4, E times s squared, okay, is approximately n plus 1/2 pi, okay? And so what does this give me? It gives me 4 over epsilon, and I can pull out and factor out a square root of e from here, which hits that square root of e. It gives me just e times the integral from 0 to 1. ds square root of 1 minus s squared is n plus 1/2 pi. So we're almost there, but we have to figure out how to do this integral. This is ds. How do you do the integral? Well, I don't know. One way of doing it is to say let s equal sine of theta, right? And so this integral is an integral from 0 to pi over 2, right? So the integral becomes 4 over epsilon e, integral from 0 to pi over 2 d theta times cosine squared theta, and that is n plus 1/2 pi. And what is the integral from 0 to pi over 2 cosine? The integral of cosine squared from 0 to pi is 1/2. But from 0 to pi over 2 would be 1/4 times pi. This is 1/4 pi. Oh, that's nice. That's pretty cool. The quarter cancels the quarter, and the pi cancels the pi. Okay, so we seem to get the result e over epsilon is n plus 1/2. Now, you understand that this result becomes valid as epsilon goes to 0. But now I'm going to make this transmutation that Tibor was referring to. Okay? Everything we've been doing is as epsilon goes to 0. But that is the same, as you see, as n goes to infinity. Okay? The left side becomes big as epsilon goes to 0. But for fixed epsilon, it will become big as n goes to infinity. These are equivalent limits. And therefore, why not just set epsilon equal 1 and take the limit as n goes to infinity? And that's the result for the harmonic oscillator. And this is very interesting. Why is this result so interesting? Yes. This is not just approximate. This is the exact answer. And this is a fact about WKB, that for the special case of the harmonic oscillator, it happens just by sheer beauty, I guess. It's just freak chance. Didn't have to turn out to be exact, but it just so happens that if you calculate the higher order corrections, the eigenfunctions will be corrected. Okay? As you go to higher and higher and higher order in WKB, the eigenfunctions will change. Okay? The eigenfunctions are not exact at this point. They're only approximate. But amazingly, the eigenvalues will no longer change. Order by order, in WKB, if we include S2, S3, S4, S5, and so on, this result will not change, and we have the exact answer. So although this is an asymptotic result as n goes to infinity, it is also exact. And that's pure chance. Just happened to turn out that way. There's no fundamental reason that is understood, at least, for why this had to happen. It just happened. So for the simple case of the harmonic oscillator, which is a solvable problem, that's what happens. Okay, yeah?
So is there like a deep connection between solvability and WKB? Or?
Yes. Okay, so there are a bunch of, I shouldn't use the word bunch because it's only a very small number, of one-dimensional quantum mechanical problems that are exactly solvable. And these potentials, over the years, they have been discovered. There are various types of potentials. There's something called an Eckert potential and so on. There are special cases of potentials which are exactly solvable. And if you take these potentials one at a time and apply WKB, what happens is, in the harmonic oscillator case, the WKB series truncates for the eigenvalue. But for these other cases, it doesn't truncate. What happens is, I was very curious about this problem a long time ago, so I wrote a paper on it. And what happens is that the WKB series becomes a geometric series. And you can sum it exactly. Okay, that's what happens in all the rest of the cases. So for the non-solvable cases, it isn't. The WKB series, there's a series that appears on the left, which is equal to n plus a half pi. That series does not truncate. It's not a geometric series. And I tried very hard to guess. I worked out some special cases like the anharmonic oscillator, which is not solvable. Stared at it for a very long time. And guess what I discovered? Very little. So you can't guess the next term in the series. Okay, so what I was hoping for was that although the anharmonic oscillator is not solvable in the sense that you can't solve the Schrödinger equation, I thought maybe you could sum in closed form. You could guess all the terms in the series. But no, it's really non-trivial. Couldn't do that. Okay, I found lots of interesting properties of those coefficients. They're connected, it turns out, with the Bernoulli numbers and with the Euler numbers. And there's all kinds of interesting numerological properties. So I wrote a paper a long time ago called Numerological Analysis of WKB. But I still couldn't guess the nth term in the series. I could find out a lot of properties, couldn't go all the way. I was a very unhappy puppy, but I published it anyway. Okay. So how about working out something a little bit more complicated? And we need to know a fact. So this is a good place to write down a fact. Okay? If you are interested in other potentials, you need to know one interesting fact, and that is that if you have an integral from 0 to 1 dt, t to the a minus 1 times 1 minus t to the b minus 1, you can evaluate that integral. Does anybody, you know what it is?
Beta function.
It's a beta function. That's right. It has the name, it's written beta, capital beta, okay, of AB. Okay, so this is called a beta function. Okay, but what is that? That's only giving it a name. That's like saying that lion, that animal over there is a lion, but it doesn't say anything. But can you tell me what it is equal to?
I think it's gamma A plus B over gamma A gamma B.
No, other way around.
Or gamma A gamma B over gamma
Yeah.
A plus B.
Gamma A, gamma B over gamma A plus B. Right. Okay. And that's a very useful fact because we know what the gamma function is. Okay. So if we wanted to use this formula for the anharmonic oscillator, okay, if we actually were interested in the anharmonic oscillator, so we could take the potential, suppose we took the potential v of x to be x to the fourth. Then, so this is example 2. Okay, there's another example. Suppose we had the anharmonic oscillator, x to the fourth. Okay. Then this quantization condition right here, the first thing we need to do is to find alpha and beta. So we need to find the solution. We need to find out where E is equal to V. Okay? So E is equal to x to the fourth. So x is equal to plus or minus e to the 1/4 power. That's where the turning points are. So this is alpha and beta. Okay, or beta and alpha, minus or plus. Okay, and so the quantization condition, this quantization condition here, reads 1 over epsilon integral from minus e to the 1/4 to plus e to the 1/4 power times, so the integral is dt, and there's the square root here of e minus the potential. Okay, so it's e minus x to the 4, e minus t to the 4, okay? And that's equal to n plus a half pi, okay? Or asymptotic to n plus a half pi. And that's the integral that we have to evaluate. So the whole problem of quantization comes down to evaluating that integral. And we're going to begin, again, you notice this is an even function. So right away I can write it as 2 over epsilon, integral from 0 to e to the 1/4 dt, square root of e minus t to the 4th, and plus a half pi. And then I can, again, same thing, I can make the substitution that t is equal to e to the 1/4 times s. So now the integral becomes a numerical integral to evaluate. So we have 2 over epsilon, e to the 1/4, and this is an integral from 0 to 1, ds, square root of 1 minus s to the 4th is asymptotic to n plus a half pi. N plus a half pi. Okay, that's the problem. So we need to know how to evaluate this integral here. And that's a hard integral to do. Okay? But in general, for when you're doing integrals like this, we would like to beat it into this form. It would be very nice if we could reduce it to a form like this, because then we could evaluate it. So that suggests another approximation. Why don't we make the, here you notice there's a 1 minus s to the 4th? And you notice there's some power here, to the square root of 1 minus s to the 4th. There's some power here, but we would like to make that 1 minus s. So the natural substitution is to let s to the 4th equal something or other, u. Okay? So s is u to the 1/4, and ds is 1/4 u to the 1/4 minus 1, du. Okay? And if we plug that into this equation here, it begins 2 over epsilon e to the 1/4. Oh, I'm sorry. There's an e in here as well. E. There's an e in here as well. Right? And that square root of e comes out front. So that gives me e to the 3/4. That's a very interesting result, e to the 3/4. And what I'm left with is an integral from 0 to 1 du times 1/4 u to the 1/4 minus 1 times the square root of 1 minus u. Did you all follow that? This is just arithmetic. Okay? So it's 1 minus u to the 1/2. But the natural way to write it is 1 minus u to the 3/2 minus 1. Because you see what we've got? 1/4 minus 1. 3/2 minus 1. Isn't that beautiful? So this becomes 2 times 1/4 is just 1 over 2 epsilon times e to the 3/4. But this integral, that's the key problem. This is just beta of 1/4, comma 3/2. And that is equal to n plus 1/2 pi. And we just got done saying that this guy is gamma of 1/4 times gamma of 3/2 over gamma of 1/4 plus 3/2. something silly, right? 6 quarters plus 1 quarter, 7 quarters. Okay? By the way, what's gamma of 3/2? Gamma of 3/2 is 1/2 times gamma of 1/2, which you say is square root of pi. Okay? We could make another slight simplification, not major, but gamma of 7 quarters would be 3/4 gamma of 3/4. But gamma of 3/4 is not expressible in terms of pi. It's just some transcendental number. So let's put this fact into this equation. Let's see what we get. We get e to the 3/4 over 2 epsilon. Then we have, on top, we have gamma of 1/4. And in the bottom, we have gamma of 3/4. Both of these are transcendental numbers. Okay? But then we have a gamma of 3/2 on top, which is 1/2 square root of pi here. And on the bottom, we have another factor of 3/4. And this is equal to n plus 1/2 pi. And once again, instead of epsilon going to 0 is the same as n going to infinity. Both have exactly the same effect. So let epsilon equal 1, because that's the problem that we would like to solve. Let epsilon equal 1. And treat this as being asymptotic as n goes to infinity. And we conclude that e to the 3/4 is asymptotic to n plus 1/2 times a bunch of numbers. And I don't have to write these numbers down. The numbers involve, there's a square root of, well, why don't we write it down? There's a square root of pi, because that combines with that. And let's see. There's a 2 in the bottom, and a 2 in the bottom, and a 4 in the bottom, which cancel. That guy, and that guy cancel. So there's a 3. And that's probably it. And then the gammas give you gamma of 3/4 over gamma of 1/4. And if we want to solve for e, we take this to the 4/3 power, and that's the asymptotic formula for E sub n, as n goes off to infinity. How about that? You notice that the eigenvalues are growing like n to the 4/3 power. For the harmonic oscillator, the eigenvalues grow like n. But for the anharmonic oscillator, they grow, for large n, like n to the 4/3 power times a number, times some constant. And that's just a silly number. Okay? So the question is, you think this is good? Let's see. Yeah?
What if we take the complex roots of x?
What if we did?
If we take the complex roots of x in the anharmonic oscillator, like take x equals...
Oh, you mean in finding the turning points?
Yeah.
Yeah. Then there are complex turning points, and we have ignored them. Okay, because they're in the complex plane, and the asymptotic analysis that we did was on the real axis. Okay, we were very careful to stay on the real axis, but complex turning points are very interesting, and they play important physical roles when you study tunneling problems. But we're not going to talk about that. Okay, but complex turning points are very, very important. If you are interested, for example, in the physics of what happens when you have a potential like this, and you have a particle beam so this is the potential, and here's a beam of particles with energy E, okay? You notice this beam of particles is going right through. It's above this potential. But suppose you want to know what really happens, okay? Classically, a ball rolls up the hill and comes down the other side and keeps going. But quantum mechanically, that's not true. Quantum mechanically, most of the particles go through, but a small number of particles are scattered back. And to find that backscattering, to find that exponentially small subdominant piece, you need to do WKB in the complex plane. You cannot do it except by going into the complex plane. And in the complex plane, if this potential is e to the minus, say, x squared, something like that, and the energy, say, is 2, then to find the turning point, you have to solve the equation 2 is equal to e to the minus x squared. And there's no real solution to this, but there's a complex solution, okay? And it's on the imaginary axis up here. So the way you do WKB, this is a one turning point problem, but the turning point is in the complex plane. So you start off on the real axis where the beam originates from the particle accelerator, okay? And then you trace this until you get to the turning point. Then you solve an Airy function problem in the vicinity of the turning point, and then you come out like this. Okay? And there are 120 degrees between here, and that's because that's where the Stokes lines of the Airy function are. So you come in at an angle, and you go out at an angle. And that, when you do the matching, you will find the coefficient of the backscattered ray. So complex turning points are very important. But in our problem, we could ignore them, okay, because we stuck entirely on the real axis.
So if we don't ignore them, does this change the eigenvalue?
No, because it gives you a subdominant correction. So it gives you a correction to this formula, which is exponentially small, e to the minus n or something like that, or e to the minus n squared. And that is negligible if we're doing Poincare asymptotics. I'm going to finish this class with a brief discussion of hyperasymptotics. Just you'll see where that comes in, but here it doesn't. Yeah.
Are the two complex turning points equivalent, or
Sorry?
there's two turning points in the
Yes.
complex?
There's another one over here, and it would give exactly the same answer.
Okay.
So we could just as easily connect from here to here,
But there's no relationship.
but we could do either one.
Okay.
It doesn't matter. Okay, you can connect to either one. Okay. So the question is this a good? I just want to, for a second, look at this. You think this is accurate? I mean, just how good is this result? You understand, we solved an unsolvable problem. Okay, this is an incredibly difficult problem. The differential equation that we just solved is this. It doesn't look so horrible if you're naive. But no one has ever been able to solve that equation in closed form. It's hopeless. It's an incredibly difficult equation to solve. Okay? By the way, you can solve it for this case, e equals 0. The solution is a Bessel function. But if e is not 0, nobody knows how to solve it to this day. Okay? Actually, somebody published a paper once in which they claimed to have a solution, and it was an immensely complicated solution in terms of elliptic functions. And he published it. It's quite a while ago. But somebody actually noticed this in the journal and looked at it carefully. And there are a lot of identities that are satisfied by the elliptic functions, because the elliptic functions are sort of complicated versions, complex, complicated versions of the sine and cosine functions. So they started using some of these elliptic identities to simplify this result. And it did simplify more and more and more and more and even more. And it simplified to 0. The moral of that story is, if you think you found the solution to an equation, plot it at least numerically. If the guy had done that, he would have gotten 0. Okay, so the question is, how good is this result? So this is what the ground state. So you understand, this answer we got is valid as n goes to infinity. So let's begin by saying n equals 0. This is going to become very good as n goes to infinity. But what about n equals 0? So this is what we find. Here is the eigenvalue problem that we just solved. And here is the exact eigenfunction, and here is the WKB approximation to that exact eigenfunction. The whole approximation consisting of the turning point problem on the left, the one turning point problem, combined with the one turning point problem on the right. So altogether, there are 5 regions. I hope you're impressed. And this is what it comes out for n equals 0. Okay? Boy, is that good. Okay? This is, of course, just physical optics. We didn't include the effect of S2, S3, S4, anything like that. Here is the second eigenvalue. So n equals 2. Forget n equals 1. We'll jump all the way to n equals 2. This is a plot of the exact solution and the WKB approximation. But it doesn't look like 2 curves unless you look very carefully. And if you look very carefully, you'll see that over here, you notice that the curve is a little bit thicker. So right around here, there's a slight, when you plot the 2 curves on top of one another, there's a slight thickening over here and over here. Maybe, I don't know, maybe a little thickening here and a little thickening over there, possibly. But you can't really see the difference. So n equals 2 is so close to infinity that you can't really ask for more. Okay? So the question is, how good are the eigenvalues? That's the equation for the eigenvalues. So here are the eigenvalues. When n equals 0, this is the exact eigenvalue. That's what the WKB formula gives. And we're 18% low. So this is accurate to better than 1 part in 5. However, when n is equal to 2, the percentage error, this is a percentage error, goes down to minus 0.56. So this is a half, minus a half. So we're off by 1 part in 200. So n equals 2 is that close to infinity. And for n equals 4, we're off by 1 part in, well, 500, roughly. Okay? 0.17% off. And you can see as n gets bigger and bigger, the exact eigenvalues and the WKB eigenvalues are becoming very close. When n is as large as 10, the error is 3% of 1%. Okay? That's really small. And this is just physical optics. Okay? Okay, so what I don't know. There are 2 possible things I can talk about, but I think we really only have time for 1. So maybe I should give you an example of an interesting new development in asymptotics, okay, which is called hyperasymptotics. And this is not something that I can go into any detail with. Okay, it's really a fancy extension of asymptotics. What it says is, the word hyperasymptotics means, okay, hyperasymptotics. This means asymptotics beyond all orders. So until everything in this course we have done, you would have to call traditional or conventional asymptotics, okay? Meaning Poincare asymptotics. That's what people like to call it. So this really means beyond beyond Poincare. Okay? So what does that mean? It means that if you have an asymptotic series of some sort, you know, y is asymptotic to the sum of a sub n x to the n as n goes to 0, then, I'm sorry, as x goes to 0, if you have some asymptotic approximation like this, if you had a subdominant term, okay, this is not equal. Why? Because there's a correction. This is not exactly equal to that. Why not? Because there's some correction like e to the minus 1 over x times some series. Okay? And this is exponentially small as x goes to 0 plus, is exponentially small compared with this, compared with every term in this series, because this exponential is negligible compared with the nth term in that series for all n. So including this term would upset Mr. Poincaré's stomach. Okay, he would get very nauseous because how can you go beyond infinity? How can you include anything beyond infinity? So I want to show you that it is possible to take into account effects that go beyond all orders. And I'm going to illustrate it with a nice, simple-looking problem. Okay? Here's the problem. Suppose someone walks up to you on the street and says, I have a really trivial-looking equation to solve. Can you solve for me y prime is equal to cosine of pi xy? I'm throwing in a pi just because it makes it a little bit simpler, maybe. This is trivial. This is a first-order equation. How do you solve it? Forget it. You can't solve it. This is much too hard to solve. Differential equations, in general, cannot be solved. Even first-order differential equations, if they're nonlinear, you can't solve that equation. Okay? But can we guess how the solution to this equation looks? Well, we can. We can guess how it looks. Because, now I want you to put on your, think a little bit. Imagine, what does the solution to this equation look like? For large x, for example. Suppose x were getting large. Can you imagine what the solution might look like? Okay, so I propose that y goes like a constant over x. Okay, now that's a nice simple result. How could this be? Because on the left side, the derivative would go like 1 over x squared, which would be approaching 0. How could the right-hand side approach 0 at the same time? Well, inside here, there's y times x, right? And y times x gives you a. So if a were a multiple of n plus 1/2, you'd have cosine of n plus 1/2, which would vanish. So both sides would vanish. Do you see that? We don't know how to solve this equation exactly, but we could guess that it behaves like this as x goes to infinity. Okay, if we guess if a is n plus 1/2, because cosine of n plus 1/2 is 0. But the only way to verify that you're not doing nonsense when you're doing asymptotics, the only way to verify that is to what? Right. We still haven't got an asymptotic balance between the left and the right side. We need a correction term. So let's guess a correction term of the form, let's suppose that the asymptotic approximation is a over x plus b over, say, x cubed. Okay? Let's just guess that that's the way it's going to work. On the left side, we would have the derivative of this, right? And the derivative of this would be minus a over x squared minus 3b over x to the 4th, and more terms. And this would have to be asymptotic to cosine of pi xy. Pi xy would be pi a plus pi b over x squared. right? But if a is n plus 1/2, and I plug that in here, I would have pi times n plus 1/2. So I know what cosine of a plus b is, right? This would be cosine of pi a cosine of pi b over x squared minus sine of pi a times sine of pi b over x squared, right? Cosine, cosine, minus sine, sine. What is cosine of pi a if a is n plus 1/2? 0. So this is 0. And when x is large, sine of a small argument is just the argument, right? Sine of x, remember, sine of x is asymptotic to x as x goes to 0, right? But this is as x goes to infinity, but it's 1 over x squared. So therefore, this is going to go like 1 over x squared. So for large x, we'll throw that away, and we conclude that minus a over x squared would be asymptotic to sine of pi a. What is the sine of pi times n plus 1/2? Minus 1 to the n. Okay, minus 1 to the n. Okay, times sine of a small argument, which is pi b over x squared, and a minus sign here, minus. So therefore, if a is n plus 1/2, then b is coming out to be, this is a balance. Everything looks consistent. And b turns out to be a, and there's a factor of pi here. So it looks like minus 1 to the n times a over pi. And we can calculate like this. And my God, this is an incredibly difficult problem to solve. I'll pay you $5,000, $5,000 reward. Okay, but we know what the solution looks like. The solution looks like y is asymptotic to a over x plus b over x cubed with these formulas, plus c over x to the 5th plus d over x to the 7th, and so on, as x goes to infinity. And you notice that a is this n plus 1/2. So what we've learned, what we've predicted, is that there are many different solutions characterized by n here. Right? So we predict. So do you see what we've done? Boom! In no time, we understand this equation. Okay. Let's draw what we think the solution looks like. Here's x. We're running off toward infinity. Here's y. That's the y-axis. And we see that asymptotically, we have many different solutions that are falling off for large x, like 1 over x. Okay? So this would be 0 plus 1/2, 1/2 over x. When n is 1, we would have 3 over 2x. Oh, that's very interesting. In fact, n plus 1/2 looks like the eigenvalues of the harmonic oscillator. So this solution is breaking up into eigencurves, not eigenvalues, but eigencurves. Okay? Then there would be 5 over 2x and 7 over 2x and so on. That's the way the solutions behave. But there's something weird here, because we could be starting at y equals 0 at any point on this axis. So what we are claiming is that what it looks like is if you start off with a bunch of points over here, all of these different solutions combine into one solution as you go off to infinity. And then all of these solutions here combine into another solution and go off to infinity or something like that. You notice there's no arbitrary constant. Everything is uniquely determined. This is a first-order differential equation. You'd think there'd be an arbitrary constant, but there isn't. That's what it actually looks like. So the solutions come together, they bunch, and they fall off. That goes off like 1 over 2x, 1/2 over x. And this is, wait a minute, that is 5 over 2x. They didn't approach this solution unless you follow them very, very carefully. There is a solution that comes right down the center here, and it approaches the solution 3 over 2x. But why did the solutions bunch up here, and not 7, but 9 over 2x, but not the other ones? Why did that happen? Say it again. Stable and unstable. Aha. Now, to understand stability, we've got to do hyperasymptotics, because this is asymptotics. If you do this asymptotics the way I just explained it to you, now I know what is a nice practice for. Is there a practice? There's not a practice this afternoon. There's not a tutorial. All right, so I'll take a second. All right. I won't leave you hanging. Okay, so there must be solutions coming out of here, but these solutions are spreading into these bunches, okay? And there must be some sort of separatrix solution here, which is unstable because anything near it veers away. But we can't see this solution here. We're going to have to do hyperasymptotics. So let's ask what happens if you have 2 different solutions in the same bunch. Okay, you understand there must be something more. Why is there something more? Because all of these constants are fixed. There's no arbitrary, there should be a continuous arbitrary constant. And we don't see it here. So I claim that continuous arbitrary constant must be in the higher order asymptotics. Asymptotics beyond all orders. So we're inclined to go and look for it. So to study stability, let's study 2 different solutions in the same bunch. y1 corresponding to n, y1 of x, and y2 of x corresponding to n. Are you following what I'm doing? Okay. Now let's look at the difference between these 2 solutions. If they correspond to the same n, of course, asymptotically, y1 is asymptotic to this series, and you can't include a higher term. But if I look at the difference between y1 and y2, this entire asymptotic series cancels out, and the only thing that could be left would be something very, very small. Smaller than any term in this series. Something maybe exponentially small. Do you follow my argument? You see what I'm doing? I'm subtracting them. That means that as soon as I subtract them, since nothing is asymptotic to 0, this must be the hyper-asymptotic contribution beyond all orders. And that's the only way I can make it visible to me. Subtract out everything in front of it. Got it? So I'll call this thing u of x, the difference between those 2 guys. What equation does u of x satisfy? Well, if I subtract these 2 equations, if I subtract the equation for y1 and the equation for y2, so take y2 away from y1, then this satisfies the equation u prime of x is equal to cosine of pi x y1 minus cosine of pi x y2. Right? But there's a formula for cosine of minus cosine of Okay, let's put this a little bit higher. Okay, what's the difference of two cosine? What's cosine A minus cosine B? So it's something like minus 2 times what? Sine of the sum, say pi x y1 plus pi x y2 over 2, right, times the sine of pi x y1 minus pi x y2 over 2, something like that. Okay? Now, for large X, what's the difference between between y1 and y2? There isn't any difference. The only difference would be at the hyperasymptotic level. So y1 is the same as y2. And we know how y1 behaves for large X. It behaves like n plus 1/2 over x. So we're adding the same thing and dividing by 2. So this would be asymptotic to minus 2 times the sine of n plus 1/2 over x times pi. And that's the sign of the difference. But wait a minute. What's the difference? That's u. Okay, so this would be sine of pi over 2 times x times u. But what is this? This guy is just minus 1 to the n. Okay? Well, that's really interesting, because if this guy is really small, this guy would be, this guy here would be pi over 2 times x times u. And therefore, we conclude that u prime is asymptotic to minus 2 times minus 1 to the n, or 2 cancels, and we just have pi times x times u. I could solve that equation. That's really easy. That's just a first order differential equation. And you notice, very interestingly, that this guy contains, this is a linear equation, so it contains an arbitrary constant. That's where the arbitrary constant is. It was hidden in the hyperasymptotic contribution to this asymptotic series. So at the very end of the asymptotic series is something that looks like this. The solution to this equation, you know what it is, right? It's just u of x is some constant, right? It's a linear equation, some constant, times e to the minus pi times x squared over 2 times minus 1 to the n. Okay? So this alternates, that's an n, this alternates in sign here. Sometimes this is getting large, and sometimes it's getting small. When it's getting large, what you have is a separatrix. Things are separating off. So when the hyperasymptotic contribution is positive, things are separating off. But when it's negative, things are coming together. Stable, unstable. Okay? Now, I know what you're going to say. You're going to say, wait a minute. You assumed, in order to make this asymptotic approximation, that this was exponentially small. All we can say is that it's growing. Okay, we had to replace sine of this by this under the assumption that it was small. Okay? So we don't know that this is really true when n is odd. All we know is that it's only true when n is even. When n is odd, this is a growing thing. It's growing like a positive thing. The curves are separating away. So we don't know that they're growing away from this separatrix curve like e to the plus x squared over 2 for large x. All we know is that they're separating away. So what's happening is, as you move off from this axis, you get sucked together, and these curves approach each other. The distance between these curves falls off like e to the minus x squared over 2 times a constant, pi, whatever. Okay? So it It gets sucked into a single asymptotic behavior, and hyperasymptotics is describing how these curves are sucked together, how they're pulled together. So all these guys are going, they're all drawn together, and the distance between these curves is falling off like a Gaussian. Okay? Everything in between, you notice they're separating away from a single separatrix curve, which is not plotted here, because I can't find it. It's unstable. But if I had perfect numerical analysis, I could draw the curve in between, and it would approach this line 3 over 2x. It would be a single curve that would make it all the way out to infinity. But one false step, if you just went like that, you'd get drawn all the way down here or all the way up here. And very rapidly, because you would go exponentially, you would be pulled away exponentially fast, okay? And pulled into the stable line exponentially fast with an exponential correction. This gives you a taste of hyperasymptotics. How did we get to the hyperasymptotics? We subtracted two solutions which eliminated all of those terms in the series. And all that was left was the hyperasymptotic contribution. See that? Do you see how powerful we are now? This problem, this is a research problem, by the way. This analysis, in fact, actually I just published a paper on this 2 weeks ago. Okay, and it actually has to do with astrophysical structure. It has to do with collapsing of binaries and things like that. But never mind. So, but this is really kind of cool because you can see the stability and the instability built into this equation, and it isn't accessible using conventional asymptotics. You have to go beyond Poincare asymptotics to hyperasymptotics to see the answer coming out. Yeah?
In quantum theories, there are non-perturbative.
Precisely. So hyperasymptotic effects are included in things like instantons and solitons. That's where the hyperasymptotic effects are. So when people say non-perturbative, field theorists use the word non-perturbative. Non-perturbative means that it's not accessible using Feynman diagrams, because Feynman diagrams give you a perturbation series in powers of g, a sub n, the coupling constant g to the n, or in electrodynamics it would be alpha to the n. Okay, that is what you get out of Feynman diagrams. These are all Feynman diagrams having n vertices. But that's not all. In some cases, many interesting cases, especially when you have topological field theories, right, there may be corrections of order e to the minus 1 over g. Okay, and this means asymptotics beyond all orders. Non-perturbative effects. You cannot calculate, you cannot expand e to the minus 1 over g as a series in powers of g. All the coefficients in that series would be 0. But you include it, one reason why you might include it is that this might be imaginary. It might be the discontinuity across a cut when you sum this using Borel summation, okay, or Pade summation. At the cut, because we know this is a Herglotz function, the real part will cancel, but there will be an imaginary part, which is a discontinuity across the cut. There it is. Okay? That is where the hyperasymptotic contribution resides. Okay? That's the meaning of that. Okay? And that's what physicists are very interested in, because interesting topological effects are contained in structures like this. And they're not accessible. You can't calculate them in terms of Feynman diagrams. You can't, they go beyond all orders in Feynman diagrams. Okay? But I thought this was kind of a cool example to show. It's a very simple example where hyperasymptotics is crucial. Okay? Any other questions? Okay. I had a lot of fun making you bored. So hope you have a good rest of year, and I hope you found it interesting. But I hope you realize that asymptotics and perturbation theory make you very, very powerful, because you can solve problems that are just hopeless if you're trying to do it the naive way, namely just solve it exactly. So all kinds of doors are now open to us. We can make progress on solving very, very difficult problems. And the solutions come out so simple. You know, that's a series in powers of 1 over x with a correction, which is a Gaussian. What could be simpler? But I dare you to try to solve this differential equation exactly. Hope. Okay, thank you.
Thank you for teaching us, giving us insight into quantum mechanics and quantum field theory. So this is
Cool.
a token of our thanks. So
Terrific.
every year we have a new version
Ah,
of this. So this is
The 2012.
So you
Classic.
can come back the next year.
And
Also,
Collect the whole
behalf of all
set.
students, here's a card to thank you for this set of lectures.
You're most welcome. I had a lot of fun. And I really enjoyed teaching you. I really enjoyed the fact that there were so many interesting questions. And I mean, that's good. That's really good. Very interesting questions. I hope you were able to follow it. Maybe there were times when things were fuzzy, but I hope you got the gist of what I was saying. So, good. Had a lot of fun.
thank you.
Okay,
Yeah.
you bet.